In an experiment, a group of children each repeatedly throw a dart at a target. For each child, the random variable h represents the number of times the dart hits the target in the first 10 throws. And Peter models h using a binomial distribution. 10 trials, probability of success 0.1. Take two assumptions Peter needs to make her model. Now we can see there's a fixed number of trials and we can see there's either success or failure. So we can't use those here. What we can do is say that we assume that the events are independent. Now, I think it's a good idea to give context to the question. Assume every child's throw is independent. It's the first one. And we're also going to assume it's not like an average of 10%, it's a fixed probability of 10%. So I think when I did this, I originally just said there's a fixed probability of hitting the target, but I kind of expanded on it a little bit after. So there is a constant probability for each child's throw. Now using Peter's model, find the probability that h is greater or equal to 4. So if you're using ClassWizard's calculator like me, we're going to need to do 1 minus the probability that h is less than or equal to 3. We want 4, 5, 6, 7, 8, 9, 10, so we're going to subtract 0, 1, 2, 3. We need to keep 4 in there. Go to Distribution, Binomial CD, Variable, 3, 10, and 0.1. This gives 0.98720. Which then gives 0.0128. I just want to remind you for how these probabilities are found. If, for example, I was finding the probability that h equals 3, then that would mean we're having 3 successes. So if you think about a tree diagram, the tree diagram just is there to help us, but it would be 0.1 cubed. And then we would get 7 failures in a row. So it'd be 0.9 to the 7. So that would be 3 successes followed by 7 failures. But then we've got to think about the different ways that you can get that. For example, you could get 7 failures followed by 3 successes, or you could mix them up. And that's where the arrangement comes in, because we're actually arranging 10 objects where these 3 are the same, 3 successes, they're all identical, and 7 failures. And there's actually 10 factorial ways of arranging all of them, but then we have to divide by 3 factorial, because these can be swapped around without any effect to the arrangement, and then by 7 factorial, and it ends up being 10C3. So that's what your calculator is working out, just for also for h equals 2, h equals 1, and h equals 0. Do remember that. Like I always think it's important. Don't just put it in your calculator and, just think, yeah, the calculator's calculating it. Make sure you understand what it's actually doing, because this can be tested. In fact, aspects of this idea are used in the next part. For each child, the random variable f represents the number of the throw on which the dart first hits the target. Using Peter's assumptions about the experiment, find the probability that f equals 5, i.e. that a child hits the target on their 5th throw. So that must mean they didn't hit it on the first 4 throws. So it would be failure, 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 and then they manage it on the 5th. And that's the only order it can happen here. So I'm using the ideas from below. It's actually called a geometric distribution. You just keep going until you get a success. So it's going to be 0.9 to the power 4 times 0.1. We don't have to think about any arrangements here. We're going to stop after that success, unless this is at the 5th throw. And that ends up being 0.06561 or 0.0656. Now, Thomas assumes that in this experiment, no child would need more than 10 throws for the dart to hit the target for the first time. Whereas in Peter's model above, actually, you could have 10 failures and then a success, or even 20 failures and then a success. It'd be 0.9 to the 20 times 0.1. But Thomas is saying no more than 10. And he models the probability that f equals n as this. This is actually like scaling linearly because it's as n increases, the probability is going to increase. We're asked to find the value of alpha. So we've got the probability that f equals 1. That would just be 0.01 actually. And then the probability that f equals 2 would be 0.01 plus alpha. And we'd carry on until we get the probability that f equals 10 as 0.01 plus 9 alpha. So I want to sum all of these up. I'm going to have 10 lots of 0.01, and then I'm going to add alpha plus 2 alpha all the way up to 9 alpha. It's actually a little arithmetic series, so you could use the formula for that, or you could just do it by hand. But remember, this is going to equal 1, because it has to be one of them. It ends up, you get 0.1 plus 45 alpha. Like one quick way to do it without arithmetic is just to write down, let's not even write them all down, but we can see that 1 and 9 add to 10, 2 and 8 add to 10, 3 and 7, 4 and 6, that gets us to 40, then we've got an extra 5. So 45 alpha is going to be 0.9 and alpha is 0.02. Brilliant. Using Thomas's model, find the probability that f equals 5. So that is then going to be 0.01 plus 4 lots of 0.02. And that's 0.08. So we're going to get 0.09. Finally, explain how Peter and Thomas's models differ in describing the probability that a dart hits the targets in experiments. That's just like a single success. And Peter's model, she has assumed a fixed probability of 0.1 because we used that at the start in the binomial and then carried it through for the next part. So we can say that. And then in Thomas's model, he's got this, well, this probability is when you're hitting it for the first time, but because it's increasing, it must be that the probability of success is increasing as we go along. So it's, what was it at the start? 0.01, but then because the probability of hitting it on the second attempt was higher, it must be that we had a failure and then we had a success. The probability of success on the second attempt must be higher than it was before. And the same for the third and the fourth. So in Thomas's model, the probability is actually increasing. And that's how they differ. So the mark scheme basically says this. Peter's model assumes the probability of hitting the target is constant. Thomas's model assumes the probability increases with each attempt.